Sorry, I didn't even ask.
Okay. Sorry, I almost forgot about you, Savannah. All right, folks.
Just no way. Well, also
We've already done the first example, but I think you can follow it, Savannah. I'm on example 2. Actually, no, I'm trying to find the alternate form of doing a derivative. A derivative is just the slope of a curve. So we used to call it slope, now we're calling it a derivative. Okay, let me remind you the concept here. If you've got just a plain old curve here like this, and we want to find, at this x value right here, we want to find the slope of that curve right there, then this right over here would correspond to f of x. If I have another point, in order to use the secant idea of connecting 2 points, if I have another point here, and it's called, and this location is x, just like this, only plus h, so that this distance is h, then this over here is f of x plus h. And so if you've got these 2 points, this point right here, if we put the points right on, it's going to be x, comma, f of x. This one would be x plus h, comma, f of x plus h. And if I wanted to find the slope between those two, I would take f of x plus h over, no, minus f of x over x plus h minus x. And that's the reason why, I mean, x minus x gives us the h here down here. So this is our difference quotient because it's like the slope between 2 points where the difference in the x's on those points is h. If we take the limit as this point crawls towards this one, that means that h is getting smaller and smaller and smaller, but not arriving. If we take that limit and use that idea, then we actually get the slope of this tangent line right there. Yeah, that's what was the idea behind the difference quotient. Now, if instead we do something like this, you can see that it's the same idea, but it comes out slightly different. I wanted you to understand that they are very, very basically the same idea. If instead I want to find the slope of at this point right here, but I'm not going to call this x. I'm going to call it a specific value a, and then I put x up here somewhere. It's not a plus h or anything like that. It's just a's here, and here's x, and I'm interested in what's going on at a. I get that point there. This right here would be f of a. This right here would be f of x. So I could pretend this thing's crawling towards this, and x is getting closer to a instead of h diminishing. But still, x is getting closer to a, right? So this is how it would look. The limit, if I wanted to find the slope of the curve at a, it would be the limit as x approaches a of f of x minus f of a over x minus a instead. You see it's the same idea? Yeah, maybe. That's the difference quotient, and the only difference is that in this one, we're imagining h on the x-axis getting really small as this point crawls towards this one. Here, we're saying the difference between these two is getting really small. X is getting closer to a. We're letting x crawl towards a, and instead of, we're just actually visualizing x closing up this gap rather than having the distance between them get smaller. It's the same idea. Okay or not? That's an alternate definition for a derivative. So I'm in the middle of page 100, and it says f prime, and it says of a, because our interesting point here, the one we're interested in, is a. F of x minus f of a over x minus a, as x goes towards a instead of h towards 0. The same concept. And it's very, very useful. This form of the derivative is very useful when your function involves radicals. It's difficult. It can be done. It's more difficult to use this form if you've got radicals in the function you wish to derive. Easier to use that one. So an easier form is a nice thing as long as you understand it's the same sort of thing. What is your deal, man?
My alarms didn't go off.
Get yourself figured out. Quit being late. All right, so I'm going to use that alternate form there to find the derivative of a function involving a radical.
That's the best thing. That's what happened. Let's make up a better excuse. Yeah, it sucks. Like, I had to help this person dying on the streets. We're in Rexburg, when does that happen?
I don't know, just say they were old.
That's not a good excuse, but the Pete Trick is on there.
I excuse me.
So what is A? What is, if I was plugging in a point, what is A?
Whatever you choose.
Okay.
What is that, 5,000?
Doesn't work. We're just gonna call it A and we're gonna treat it like a constant.
How does that work?
Okay. All right, so I'm gonna say that this is gonna be the limit as x approaches A. I'm using the alternate form of root x minus root A. Does this sound reasonable? Over x minus A. That's just using that alternate form over there. Are you with me or not? And now I'm going to show you a trick, and this is a trick. Don't let me tell you it's not. It's a trick because you've never seen this particular use of what I'm going to show you before. But remember it. Try to put it in your memory and your repertoire of possibilities for doing a problem. We are not going to, usually you rationalize the denominator. We're going to rationalize the numerator.
Well, that's fun.
Do you remember how to rationalize things? Do you remember how to rationalize the denominator that involves radicals?
Yeah.
You do?
Times it like X minus 8.
Yeah, you times it by its conjugate. So I'm going to multiply this fraction right here by 1 in such a way that my denominator or my numerator will turn out rational. So I'm going to multiply it by root x plus root a because that's the conjugate of what I wish to rationalize. I'm just doing it to the numerator. So on the bottom, I have to multiply it by root x plus root a. So I'm really multiplying by 1. You okay with this?
Yeah.
All right, now watch. This is a really good example of why you do not FOIL out your denominators. You leave your denominators factored. We do want to FOIL the numerator because that's the whole objective, is to get rid of the radicals. And we do that with a conjugate. So root x times root x is x. Root x times root a is root xa. Negative root a times root x is negative root xa. Gone. Negative root a times positive root a is
Negative A.
Do you see something happening here? Okay, so I'm going to have in the denominator x minus a times square root of x plus the square root of a, and these now will cancel. That's nice. Now what I'm taking is the limit as x approaches a of 1, there's only 1 left, over root x plus root a. Is it okay to let x arrive at a now? It wasn't here. If x arrives at a, you've got a minus a, and that's 0. But could I do it here? Yeah. That would be 1 over root a plus root a, which is 1 over 2 root a. Now you have a slope generator because Jacob asked, well, what is A? Well, A is anything you want. It's just that the slope generator ends up being in terms of A. It's still like being in terms of X. You just choose the A you want. It's your slope generator, yes?
Do we have to rationalize that denominator?
No.
Awesome.
You may see that in the solutions manual once in a while. And the reason, and it's not necessary, the reason why you see that in the solutions manual sometimes and not others is because they have about a team of about 8 or 10 graduate students making up that solutions manual once they write the problems, and they're all doing it differently. So this is what I always say, well, how far do we go? Well, any correct answer I will give you credit for. With the exception of, you have to simplify radicals like root 20 has to be 2 root 5. You can leave radicals in the denominator, and you also have to simplify fractions. Do not give me an answer that's 4/8. You reduce it to 1/2, that will cost you, because that's ridiculous at this point in your life. Okay? All right. So you may leave it like that. And this is the slope generator. In other words, f prime of x in terms of x is 1 over 2 root x. If you want to leave it in terms of x like this, all you got to do is change the a to an x so that these two match. So we have the derivative of the square root of x is 1 over 2 root x, and it's a function of x. Yes?
How can we just switch the x and the a, right, different times?
Because, and I erased it so that I could do this problem. Do you remember the graph of the other one? X was our point of interest. We just made A the point of interest so that we could crawl towards A. The variable doesn't matter is what I'm saying. X is coming towards A, the other one, X plus H, was coming towards X. It's all arbitrary. As long as you're getting closer and closer and closer, you're closing up the gap. That A,
You can put Z in there.
what? Oh yeah, you could put, a D is not a good one, you'll see why in a minute. But just about anything else you put in. You could put, somebody said, well, you could put 4 in there. No, you can't. It still has to remain a variable so that you can generate other slopes. Okay? Okay, here's an interesting thing to note though. Can anybody tell me what the domain of this function is?
0 to infinity.
Is 0 included?
Yes.
What is the domain of our derivative function? No.
Not including 0.
Strictly greater than 0. So the domain of the derivative is slightly smaller than the domain of the original function. That can never be reversed. Now, quite often their domains will be the same. But the derivative's domain cannot be bigger than the original function's domain. It can be smaller.
That's like no slope at 0.
Yes, and here's why. If you think about what the square root curve looks like, I'm going to put it over here, so because I'm running out of space. What does the square root curve look like?
That thing.
Yeah, it looks like a half a parabola opening outward, right? Like this. Well, right here is 0. If I had drawn it just perfectly, which is difficult to do, right here is 0. If you draw a tangent line there, what kind of line is it? Vertical. What is the slope of a vertical line?
Undefined.
Undefined. So the derivative cannot generate a slope of 0 because that slope is undefined. Besides that, the derivative has the possibility to divide by 0.
Because 1 over 0 is undefined.
Right. So it's the slope there because it's a vertical line.
Your mind is wrong.
It's all lining up. Okay. Next thing. Talk about notation. In any language, if there are multiple words, multiple synonyms for an idea, it's because the society that speaks that language holds that idea in high esteem, high regard, much, value to it. For example, the concept or the idea of love. You have affection. You have endearment. You have all kinds of things. I mean, if you look up synonyms for love, it's a lengthy list because we value that idea in our lives in all sorts of different contexts. The same is true in math with the idea of slope. You have no idea how important that idea is, that concept. We have the word slope. I put equals in between because these are synonyms. Slope, rise over run. Shh. Can you give me another idea for slope? M. Rate of change. Anything else? How about a formula? No, that's a
Y
line.
minus Y. Yeah.
In physics, you'll see this a lot. It means the change in Y over the change in X. That's what differences are, is a change in. You will also now see this. And this.
Wait, what's that?
And this. And this.
What are all these?
These are all different forms of derivative.
Oh,
This is the only one you see. You'll also see this. And every one of these ideas, many, many different ways of expressing it, means slope. Slope. An extremely important concept. You'll see some of these notations at the top of page 101 if you look with me. This is how you pronounce these things when you see them. The first one is Y with a looks like a foot symbol, but it's not. We say that's Y prime. just like you've heard me call it f prime. Y prime is a nice and brief, but does not name the independent variable. We don't know if y is written in terms of x, or p, or q, or t. So it doesn't mention the variable it is written in, and that can be important sometimes. dy over dx is pronounced dy dx. We do not say dy over dx. You two take the conversation out in the hall if you want. Anyway, dy over dx is pronounced dy dx for sake of brevity. Or the derivative of y with respect to x. When you say it like that, then you know that y is the dependent variable and x is the independent variable. If they said dy dt, then t would be the independent variable along the x-axis. Okay? This names both variables and uses d for derivative, little d. df dx, or the derivative of f with respect to x emphasizes the function's name. It could be dp dt, which means the change in population over time. Whatever the dependent variable is, and it is on the top, is d of that over dx. And then we have d dx of f of x. This emphasizes the fact that you're taking the derivative of f by sitting it out there. It's just like putting it in the numerator. It's just that, as we're saying, find the derivative of f with respect to x. Anyway, you will see all of those. You will see, don't mention which we have mentioned before. You will see this one a lot. It not only mentions the variable for which we have to derive with respect to, but it's a quick way to write we're deriving the function. These other things with little d's also mean we are deriving. Now, Newton, when he was coming up with this stuff, I'm not kidding you, there's pictures of him. I don't know, they're not photographs, it wasn't too early for that, but they're what people imagined him looking like. He lived in a little kind of a sort of basement apartment, very, very small, one room, had a stove, and a cot, and a place for him to spread out all the stuff that he was doing. He had a lot of papers to write on, ink, that kind of thing. And it sat above, it kind of reminds me of Mr. Kruger's Christmas. It sat with a window at about ground level. The window was just above it, and you could see people walking by. And it was a hole in the ground that looked like a potato cellar. Didn't even have bricks or boards around it. And for most of his time, he spent, after he became they knighted him. They gave him a better place to work after that when they recognized his brilliance. But until then, he was only interested in doing his own little lamp, and that was about it. And he would work by that at night, sometimes during the day, because he was in this little hovel. And he would do his work, and he would write down everything that he thought in using his own notation and his own language. And if you couldn't understand him, then you weren't worth talking to. He's kind of an arrogant son of that. However, he did say one time, I've only accomplished these things because I stand on the shoulders of giants. So he at least acknowledged the people in mathematics and calculus, and not calculus, physics, up to that point, said, I've taken what they've done and expounded on that. Thank goodness for that, is what he was saying. Okay, he was kind of I don't know, he was arrogant. And he communicated with several people all over Europe, but only if they could understand what he was saying, and only if they could follow his lingo, which was difficult. You had to study hard to get it. He called derivatives fluxions, and he called integrals fluons, or vice versa. I can't remember which one. Fluon. No, I think it was fluxions and fluons. Not sure why he called them that, but and that's why they pronounced it in English. They became derivatives of integrals because the other guy in Germany, Gottfried Leibniz, he was an aristocrat, born to the nobility, always lived well. But he also had correspondence all over Europe. He tried corresponding with Newton. He tried to be nice to him, and Newton said, nah, I haven't got time for you. And Leibniz was extremely interested in making certain that the people that he communicated with could understand what he was doing. And he went to great lengths and pains to make sure that the way he wrote things and the way he expressed his thoughts was well thought out and well written. And we use his notation today because it's easier to understand. I want to read you a little bit about him. He's pretty cool. Leibniz. He's also very arrogant because he was a member of the aristocracy. He didn't have any tolerance for poor people, unless they could think. And a lot of them could, but I don't know, a lot of them didn't have the opportunity to. They were busy trying to figure out where that nail was coming from. Okay, so this is 17th century. People are struggling. They're just coming out of, the Dark Ages. They've been at it a while. So here's Leibniz. Remember, he lives in a really well-apportioned house. Some might call it a mansion. Okay, and he's not quite my age. He's a little younger than that. I'm not going to tell you what my age is. So this little blurb in here is called Leibniz Meditates in His Room at Night. Listen up. Sitting in his study in Hanover, the brown-walled room close from an elegant and very efficient porcelain stove, he must have first said to himself, rehearsing the obvious points as he adjusted his plump posterior into his ornate wooden chair, vellum sheets spread before him on a leather-covered desk, that speed involves a change in place and a change in time. And here, Leibniz moves his fleshy right hand in front of his face in an arc from left to right, palm inward, his hand pivoting on his elbow, as if to remind himself that as it has flesh and blood, some tangible thing in the real world has speed. It is well past midnight, the deep quiet of the provincial city seeping into the sepia study. Do you know what sepia means?
No.
You've seen sepia pictures, I'm sure. They're not completely black and white, but they're different hues of brown.
Oh, yeah.
So a sepia study is filled with browns, like a man cave would be. Sort of, kind of, usually, okay? So when it says seeping into the sepia study, imagine him sitting there and there's just, the carpet is a shade of brown, the curtains are brown, I mean, everything's different shades of brown, okay? Just get a feel for what he's doing. Okay, listen. Shh. Clock chimes the quarter hour. A feeling of intellectual fullness comes over Leibniz, a calm sense of his own mind's spaciousness. The arc that Leibniz has been tracing with his hand, he contracts so that only half the distance is covered in the space before his face. He leans back into his chair and holds before his attention like two rattled courtiers. Do you know what a courtier is? Someone who basically comes to pay homage and hope get you in your good graces. Okay, so try it again. The arc that Leibniz has been tracing with his hand, he connects so that only, where was I? He leans back into his chair and holds before his attention like two rattled courtiers, those two abstractions, change in place and change in time. The sounds of the faraway clock are routine and reassuring, the regular division of the temporal continuum, one point following the next. He holds his hand steady, his fingers relaxed. In moments such as this, Leibniz has a tendency to address himself. What, he asks, is the speed now? His thoughts move slowly through the great room of his mental powers. He realizes he has always realized the discordance between speed, time, and distance. Beneath the appearance of contradiction in these concepts, he senses some scheme of reconciliation. He knows there's something. He's been thinking about it long enough. He knows there's something. Yeah, spacious mind. Okay. The steady rhythmic ticking of the clock prompts Leibniz to imagine the sounds suspended in space. He has to see what he hears, each gentle tick breaking open before his eyes like a small multicolored burst. He attends to one such burst, the sound or the sight marking the moment as it arises and then perishes. And with the thumb and the forefinger of his left hand, he measures the distance between that sound, which has already vanished, and the one to come. And for a moment, he sits in that strange position, his right hand descending in a gentle arc, the fingers of his left hand measuring the time, drawing close to one another. Whatever the distance, he thinks, half forming the words, thinking almost in images, it is yet some distance that my hand has moved. Whatever the time, it is yet some time that my fingers have measured. To be sure. And yet, what if the distance between times were to become small? How small? Leibniz asks himself. The clock chimes, and as it does, Leibniz taps the table with his thumb. This is now, he says. With great delicacy, Leibniz allows his forefinger to approach his thumb. Very small. He can sense in the skin between his fingers the contracted space between his flesh. infinitely small. He sits like that for a heavy moment. Meaning what? The distance between times is infinitely small. Yes, infinitely small, but still, it is not nothing, that distance. And if that distance is not nothing, it must be represented by a number. Not a genuine number, he thinks, adjusting his thoughts to account for his own audacity, but a useful fiction, an imaginary object. Don't not going imaginary numbers, don't panic. And it must be smaller than any other number. Is it zero then? No. That would make nonsense of everything. Division by zero is an invitation to the black hole of meaninglessness. Smaller than any other number, but yet greater than zero.
Who wrote this?
Berlinski. Listen. Interesting, he's saying, but greater than zero. Interesting. An infinitesimally small number measuring an infinitesimally small distance in time. Leibniz eases his legs underneath the table. Infinitesimally small numbers. His eyes are heavy. The hour is late. There were times when he would sit like this through the night. And why not, after all? For a moment, he lifts his head as if to address an audience. He maintains contacts throughout Europe with over 200 correspondents. At night, he imagines that he is conversing with them. At the one end of things, the natural numbers, 1, 2, 3, 4, 5, form an infinitely large progression. Why not a compression of numbers so intense as to be the inverse of infinitely large? It is a large step to take, but beyond this step, he can see the rest of the calculus begin to unfold. In such situations, Leibniz thinks, it is only the first step that counts. Leibniz raises his hand again, traces an arc from left to right, and from right to left, and holds his hand steady midway through the arc. Taking up his heavy gold pen and smoothing out the gray vellum sheets with the linen cuff of his sleeve, Leibniz writes the symbol T, little t. This stands for the time now, he says emphatically to himself. Then he writes the symbol little d. Now let dt, yes, let that be the infinitesimal difference between time now and the next moment. With the unself-conscious mental habits of a man used to abstractions, Leibniz allows the soft crown of his study to the superb walnut desk with its rich inlay of ivory, the drapery-covered walls broken by former portraits of his patrons, the yellow and white porcelain stove to dissolve, and imagines instead the axes of a coordinate system stretching in front of him. The origin, he realizes with a soft smile, aligned precisely with his large nose. Dipping the quill of his pen into the crystal inkwell, he then writes the symbol D, little d, little y, right next to each other. The symbol dy on the vellum sheet. The pen making a soft scratching sound. Now then, he says sternly to himself, if dt is an infinitesimal difference in time, I must say that dy is some infinitesimal distance in position, difference in position. That's what that should say. How far my hand has traveled in an infinitesimal amount of time. Leibniz moves his hand in its now familiar arc, imagining that it is representing changes on the y-axis of the coordinate system. But now he tries to make the movement of his hand constrained. So he notices, as he does, a slight tremulousness along his fingers. He sits there, a large, portly man in a brown room, staring at a coordinate system. The coordinates fading finally into the warm sepia of the room itself, long shadows lit by a single candle. Then Leibniz writes the symbol, dy over dt, on his vellum sheet. He has always believed in the power of symbols. Good symbolism is one of the greatest aids to the human mind, he says, quite aloud, quoting himself, addressing his congregation of European correspondents. He fixes his attention on the symbols, dy over dt, allowing them to form and reform, the letters separating from one another, elongating themselves, and then he draws a heavy black line underneath the symbols. The ratio of a change in place during an infinitesimal change in time. This, he says, is the speed of an object that is traveling at an instant t. The great wooden grandfather clock in his downstairs hallway tolls the hour, and the last mournful chime reverberates. Leibniz imagines. He actually sees time moving forward from that chime by an infinitesimal amount, a tiny dimpled hiccup in its everlasting forward flow. He looks down to consider again what he has written, the letters, dy over dt. The first of the great symbolic forms of the calculus has taken shape on those vellum sheets sometime late at night, sometime late in the 17th century.
That's deep. So, why don't we just use 0
What?
instead of H?
Why can't we just use 0?
Yeah.
You can't divide by 0.
Yeah, but you don't have to, because what if you just went long enough to where you could cancel it out?
Well, that's the beauty of using algebra to do it. And we have only given you problems where the H cancels out. There are problems where it doesn't. And you have to think more like Leibniz in those cases. Think we've pulled it all off by manipulating algebraically the things I've shown you so far. Those are familiar, easy to handle things.
Oh, that's good.
Okay? This is what chapter 3 is about, is handling the difficult stuff. We'll get there slowly. Not gonna make you. Don't panic. You'll be all right. Anyway, sometime I will read you about the next part that says the future rebukes the past, but not today. Okay, so these symbols that you see here have evolved from his original dy dt because he was only interested in time elapsing. We now say dy dx because sometimes the x-axis is not time. Sometimes the x-axis is the demand curve in economics or something. Okay, that's not the demand curve, but something that is not time. Okay, now let's get back to first and see if you can follow this. The question was asked by Connor. He says, if this is a function itself, well, if this thing, this slope generator, turns into a function of x, are the original function and the derivative related in some way? Is there some way we can predict one from the other? The graph of it, there is. Take a look, because this is your first experience here. Don't worry if you're struggling. If you're struggling some and your mind's not quite wrapping around it, time spent on task will help you with that. Just deal with the discomfort. I will help you through it if I can. Look at example 3. It says, graph the derivative of the function f, whose graph is shown in figure 3.3a. Discuss the behavior of f in terms of the signs and values of f prime. Now we're starting to tie the two together. And this first experience is not easy for most people. So the first graph we're looking at is the function. And the reason why they show that black line right at A is to help you count out and remember that from A up to the top of that black line, you would have to count up 4 and over 1 so that the slope of that black line is 4. Pretty steep. Would you say that the slope at B is also 4? More or less? Less. Would you say that the slope of C is smaller than the slope at B? As a matter of fact, you know what the slope of C is. What is it? 0, if that's at the top of the curve, and we believe that it is. Would you say that the slope of D is as big as B? Certainly not. As a matter of fact, the slope of D is less than the slope of C because it is negative and we've gone left down the number line to get to it. You following? So people sometimes look at B and D and they say, no, the slope of D is not smaller than C. Yes, it is. It's negative because it's leaning left. Would you say that the slope at E is about the same as D? I mean, they're telling you where it is. Look at it. Slope at D and E are about the same. Would you say that the slope in between D and E ever got to be less than -1? Maybe. I mean, it looks pretty linear, but probably a little less. And look at F. The slope at F is 0, just like it is at C. Now we're coming back up as we start to turn the curve again. What you are seeing in the curve next to it is a graph with the same x values, but the y values have now become slopes. Notice that when x is 0, the slope of the curve at 0, and the first curve, that slope we decided was 4. Notice that at the same x value of 0 on the y prime curve, the value is 4. It's the value of the slope.
Yeah, so it's just a graph of the slopes, like just graph the slopes.
Where the y values are the slopes of the original curve at the exact same x value.
That's cool.
It is cool. Wow.
Wait, so if the first one, if A was like an x cubed function, the derivative would only be like an x squared function?
Yep. You're starting to see it. You're starting to pick up on things. This does look like a cube function. Looks like you could fit a cube to it pretty easily. And notice that the derivative curve is quadratic in shape. Okay, and notice that as soon as we hit C, which is at approximately x equals 2, that when you look at the derivative curve at C prime, still x equals 2, the slope of the original there is flat. So we plot that as a 0. Then between C and F, all of those slopes are negative. So the slope curve values are below the y or x-axis. Does that make sense to you? Returns to 0 at F, and apparently, at least what we're seeing, goes up from there. So the derivative curve goes up from there. Notice the two slopes at D and E are 1. Oh, excuse me, -1. So we have D prime and E prime at -1. The reason I asked you, between D and E, do you think it gets any steeper? Based on the derivative curve, it does get a bit steeper, because that curve shows a value that's a little bit less than -1 between D prime and E prime. Are you following? You sure you got it? Excellent. Now, this is what we were supposed to do. Oh, no, we've already done all of that. We discussed it, F prime in terms of F. Okay, now turn the page. You should have a Post-it at the bottom of the page. Do not look under it. Don't look under it. Anybody else? You have a Post-it? Okay, that reflects his. Look at that curve. Okay, don't look at it. You'll do yourself a disservice. Don't look at it.
Why?
Because don't do it. Just don't. Don't try to see through it either.
I heard it. Sam, you did yourself a service. I didn't do it.
Okay, don't look under it.
I want to.
Okay,
I want nothing more.
before we get to that one that's got the Post-it, don't be nice like Christmas, don't look under it. Don't open that package. Okay, we're gonna do exploration 1 first, which has nothing to do with it. Look, okay, exploration 1 first. Go back to the previous page and that thing we just looked at, and let's see if we can give some context to what we're looking at. So you guys look at those two curves while I read this exploration to you on the next page. It says, suppose that the function in 3.3a represents the depth in inches of water in a ditch alongside a dirt road. Doesn't have to be a dirt road. He's just trying to give you a picture. As a function of time, x in days. So x is in days along the x-axis, and y is the depth of a ditch of water in inches. How would you answer the following questions? Here's the question. What does the graph in 3.3b represent?
How fast it was filling up? Not filling, reverse filling up? What's that called?
Draining.
Draining. Thank you.
Reverse.
Reverse filling up.
That's fine, I understand that. How fast? You think he's right? It represents how fast?
Or how much?
How much water?
No.
How much water is represented by F? What does F prime represent? It is how fast. There's a rate.
You made it sound like I was wrong.
No, I know, I just want to be sure. Fast is fast is another way of saying how fast something is happening is a rate,
3.3b.
right? So what do you suppose in 3.3a, the function itself, what do you suppose the units are? No, I'm marking up wrong here. What do you suppose the units are for, what does the x and y axis represent in F prime? What does the x axis represent?
X is still. I know it's still time.
X is still time in days. What does y represent?
The speed, the rate.
It's measured in what?
Day, whatever. Inches per days. Whatever.
Excellent. Inches per day. The y-axis in F prime is inches per day because the slope is the change in y, which is inches, over the change in time, which is days. And that is a slope generator, dy dt. You following? Okay, so the y-axis on the slope generator side is inches per day. 2, this is the second question. Describe as carefully as you can what happened to the water in the ditch over the course of the 7-day period. Who wants to, as carefully as they can, describe what happened to the water? Start out with the words. On day 0, when we started the clock, the water was 1 what? 1 inch deep. Continue. Be sure you're looking at the slope graph as well as the original graph, and you give me your descriptions. What happened next?
Started filling up, but at the same time, something else was making that filling up slow down.
That's an excellent way to phrase it. It was filling up. What evidence do you have that it was filling up between day 1 and day 2? Between day 0 and day 2.
Values of A go up.
The values of the original function go up. What causes you to believe they're going up slower and slower?
As the derivative is going down.
The rate of change is going down. Very good. Very good. Continue. After day 2, what happens?
Peaks at day 2.
Pardon me?
It peaks at day 2.
It peaks at day 2 at what depth?
It's no longer filling.
At what depth?
4 and a half. Between 4 and 5.
Between 4 and 5 inches. Okay, so that's it filled up to there, and then beginning on day 2, it begins to what?
There's a derivative of the derivative.
Absolutely. What does it do? It begins to empty. Is it emptying faster or slower between day 2 and 3?
Slower. Derivative
Is it emptying faster or slower between day 2 and day 3?
Oh, yeah, it's speeding up.
It's emptying faster and faster. What evidence do you have of that?
The slope. The derivative gets lower and lower.
Yeah, the derivative is getting lower or farther away from 0 in the negative direction. So it's draining faster and faster until when?
So therefore,
And what happens on day 4? Is it still draining?
yes, that's faster.
How do you know it's draining?
From both functions, the derivative is still below.
The original function's coming down, but the derivative is still negative. When the derivative is negative, your rate of change is dropping. I mean, sorry, not your rate of change. Your values are dropping when the slope is negative. That makes good sense, right? Decreasing. The original function's decreasing.
Yeah.
Until when?
Day 6. Day 6.
Day 6. What happens on day 6? Starts filling up again. From what level?
1 inch.
1 inch about, okay? And it starts filling up again, and then after that, we don't know for sure what's going on. But you have evidence that it starts filling up again, not only because the original graph starts going up, increasing we call it, but the derivative, okay, let me ask you this. After day 6, from day 6 on, is it filling up more quickly or more slowly?
Quicker.
It's getting quicker and quicker. What evidence?
The slope of the derivative is up.
Not the slope of the derivative. The derivative, which is the slope of the original, is getting bigger.
Okay.
So it's filling faster and faster. Everybody clear?
Yeah.
That's pretty crazy. All right, now I want you to turn a page. Don't look under your Post-it. Look at the graph to the left of the exploration. This is a different thing. This graph actually belongs to example 4. And it says this. You get the graph that you're looking at, that you can see. And this is the stipulation behind it. It says, sketch, by the way, look very carefully. What is this a picture of?
Which one? 3, 4.
Yes.
This one is.
It's the picture of a derivative of something.
Oh.
It's the picture of someone's derivative.
Oh, great.
So you're looking at a derivative graph,
On which graph?
the one that you can see.
The one above.
Yeah, 3, 4. Look at it carefully. It says y prime, which equals f prime of x. You're looking at a derivative. Possible. I'm not asking you to put any context to it. I want you to realize, though, that you're looking at a derivative graph. What we want to do is recover the function whose derivative is this, with these particulars. F of 0 has to equal 0. Okay. That has to be a point on the graph. That's one thing that has to happen. Another thing that has to happen, the graph of f prime, the derivative of f is shown in 3/4. So we get that information. And f is continuous for all x. That means that when we are done drawing the graph that I'm going to put on this grid, it has to be such that we can draw it without ever lifting our pencil. So what do you know? I mean, if you go from left to right in the graph that you can see, What does that tell you? Pardon?
It stays on the same line, so it has a constant rate.
A constant rate. When we're graphing, that's called a constant slope, yeah, which is a line. And what slope does this line that we intend to draw have?
-1 and then 2.
Yeah.
-1 and then quickly jumps to a slope of 2, but must be continuous.
So it's usually eastwise.
Yeah, so it's, and it has to go through this point. Where does it switch from having a slope of -1 to having a sloping of 2? What x value? At 1. So here's 1. I got to switch there, but I have to go through this point. So if it has a slope, what does it have before this?
But it has to go
What
to
slope
the
does it have? Yes, it says so in the
Oh,
question.
okay.
Yeah.
So it's just.
It has a slope of -1 until it gets to here, right? And it has to go through this.
So it's just, yep,
And we have to continue that slope until we get to 1, and then what happens?
it jumps to
It jumps and has a slope.
slope of 2.
Is that what the?
And it jumps immediately. So just because your derivative curve is discontinuous doesn't mean your original has to be, but it does mean that it jumps from one slope to another immediately, and that's called a corner. We will learn more about that tomorrow.
So
Now look underneath there, but don't unhook us, because every time you do, the adhesive gets less. See, it's exactly what you thought.
Wowzer.
But I wanted you to build it without seeing what the result was from what you had to, determine from the brain.
that's just like,
Okay, there's just time enough to get through. I don't think I'm gonna get them all done, but you'll have plenty to get going on your assignment.
Yeah.
I wanna talk to you about another kind of derivative. Do you notice the title of your book? What's it called?
Graphical numerical algebra.
Calculus, graphical, numerical, and algebraic.
30.
We have looked at graphical examples, that's what we just did. Graphical representations, we also looked at graphical representations here. In example 2, with the radical, we did algebraic. A new trick you learned, rationalizing numerators. Oh crap, I forgot we were out today. We'll learn about this tomorrow. I'll finish it up tomorrow.
Okay.
Bell ring, sorry Savannah, we'll finish this up tomorrow, bye.